talk about error analysis. First off, let's see what's going on in a figure. So let's let this be the probability density function of the filter output. And let this be the filter output. So if a 0 was sent, so this is actually conditioned on a 0 sent. If a 0 was sent, the mean is NB. And the variance is NB times N0 2TS. And we have a Gaussian probability density function. So if you'll recall, when we talked about this example last class, we said NB, that's what happens if 0 is sent, minus NB, that's what happens if 1 is sent, that's without noise. So we argued that probably a good idea to set the decision threshold between them. We call that Z. That's 0. So what happens, what could happen if we cause an error? If the threshold is here, then if I'm to the right of the threshold, if I'm greater than the threshold, in this region the decision is correct. So if the 0 was sent and the output of the filter is greater than 0, then I decide a 0, so that's correct. If a 0 is sent and the output of the filter is less than the threshold, less than 0, then over here I decide a 1, so therefore the decision is an error. So in other words, the probability of error given that 0 was sent is equal to the probability that the filter output phi is less than the threshold Z. So this is equal to, because the filter output phi is a Gaussian random variable, this is equal to the integral from minus infinity to Z of the probability density function of the filter output, given that a 0. So what is that integral? So if a 0 was sent, then what is my mean? My mean was NB, and my variance was NB N0 2TS. So f of phi, given that 0 was sent, I argued this is a Gaussian random variable, so its probability density function is this. It's 2 pi sigma squared e to the power of minus 1 over 2 sigma squared pi minus mu squared. And if I substitute everything in, 1 over root. Actually, I'm going to leave this as sigma. I'm going to keep that symbol and just substitute the mean. Okay, so now we have to integrate that from minus infinity to z. Okay, let's, before we consider that, let's examine the case where 1 is sent. 1 is sent, here's my diagram. Now I have a mean of minus NB. It's still a threshold of 0. So now, the probability of an error, well, over here I'm deciding 1. And over here I'm deciding 0. So if a 1 is sent, the probability that I decide is 0 is the probability that I make an error, which is this probability here. That's integral from z to infinity of the probability density of phi given 1 is sent. If a 1 is sent, then my mean is what? Minus NB. And my variance is NB 0 over 2TS. So that's the same as in the 0 case, so I'm just going to keep that as sigma squared. So therefore that's equal to the integral from z to infinity of 1 over root 2 pi sigma squared e to the power of minus 1 over 2 sigma squared phi minus phi plus NB squared. Okay, so I can tell you what's the probability of error given that a 0 was sent, and what's the probability of error given that a 1 was sent. So the average probability of error, putting that together, the average probability of error, if I know the probability of error given 0 was sent, and the probability of error given that 1 was sent, how do I find probability of error given these two? You can add them, but you have to weight them. How do you weight them?
From minus infinity to infinity?
Probability of error into the probability of 0 and divided by probability of 0.
So generally speaking, if you have f of a given b, and you want f of a, you sum over all b, f a given b, that's f b. In other words, you sum over them, but you weight them with respect to the probabilities of each of them. So probability of error given 0 cent times probability 0 cent plus probability of error given 1 cent times probability of 1 cent. In other words, if we can solve these two integrals, we can know what the average probability of error is. Let's look at this integral because it's easier. Or it basically eliminates one step. So not hugely easier, but a little less confusing.